This math talk is just a continuation of our previous math talk that introduced the concept of a prime number. And it begins with the task of stating which of the following numbers are prime. So we're looking at the numbers 18, 23, and 51. Now, if you recall from our definition of prime numbers, we said that prime numbers are natural numbers greater than 1 that are evenly divisible by 1 and the number itself only. There are no other divisors, or no other numbers can be divided evenly into that number. And we discovered in that there was just a single prime number that was even. That was 2. All other even numbers were built from that 2, or had a factor of 2 in them. So right off the bat, without having to do any work, I can eliminate 18 as a prime number. So I'm going to take that out of the mix. It is not prime. Now, when I look at 23, it might be easier if I look at a multiplication table. So consider this. I have the multiplication table for 1 times 1 up to 12 times 12. And as I look within that table, if I were to look at all the numbers, I would not find the number 23. So right now, from the looks of things, it looks like my only factors are 1 and 23. So 23 is feeling prime. But there is also a bit of a way to look through this in a more efficient way. I don't really want to have to look through this entire table. And in fact, this table does extend beyond 12 times 12. So here's what I do to maybe shortcut my work. I consider 23, and I say to myself, okay, what is the square root of 23? Well, the square root of 23 lies somewhere between 4 and 5. So it's 4 point something. Now, before I build on that, let me go back to the 18 that we had. We said 18 was even and therefore could not be prime because it was greater than 2, being the only even prime. Well, let's take a look at it. Here I have 18 in my table, and you can see that that's the product of 9 and 2. It's 9 times 2. Similarly, 18 appears again here, and it is 6 times 3. So we look at it this way. We say 18 has factors that are 1, 2, 3, 6, 9, and 18. Now you'll notice something very interesting about this. The square root of 18, well, coincidentally, is also 4 point something. 4 point something. Well, if we were to locate that amongst the factors, 4 point something lies in here. This is where the square root of 18 lies. It's somewhere in between the 3 bottom factors and the 3 upper factors. And so if we're looking for factors of 18, we will get factors both below and above its square root. So if we haven't found a factor by 4, then there aren't any factors above. So we really only, for 18, have to test 1, 2, and 3. Well, the same thing is true for the square root of 23. If there are going to be factors of 23 other than 1 and 23, our only candidates are 2 and 3. When I look at my 2 times tables, no 23 in there. In my 3 times tables, no 23 in there. I'm going to point that out one more time for you. Let's consider a number like 16. Well, 16 has factors that are 1, 2, 4, 8, and 16. Well, guess what, folks? That number right there is the square root of 16. Once again, we have 2 factors below, we have 2 factors above. You will have factors below for every factor that you have above. So if I was trying to find out the divisors, or the numbers that divide evenly into 16, I'm looking at numbers below the square root of 16 as possible candidates. If I haven't hit anything by the time I hit the square root, there aren't any options above that. Moving on to 51. Now 51 doesn't appear anywhere in our table either. However, 51 is a bit deceiving. If you extended our table out to, instead of 12 columns, to 17 columns, you'd see that 51 is 3 times 17. So in fact, 51 has factors of 1, 3, 17, and 51. Just as a side note, the square root of 51, which is 7 something, lies in between. So again, 2 factors below, 2 factors above. So in our discussion of prime numbers, of these numbers that have been listed, 23 absolutely is prime. 51 absolutely is not prime. Does not fit our definition. Now we're going to extend the challenge just a little bit. We're going to try and find all prime numbers less than 100. And I'm going to show you a really, actually clever technique for finding these. Watch what we do here. So our problem becomes find all prime numbers less than 100. Now I've put together all the numbers 1 to 99, so really all the single-digit and two-digit numbers into a table. And if you take a look at them, they are arranged in a particular way. I've created 6 columns. The columns are numbered 1, 2, 3, 4, 5, 6. The next row would be 7, 8, 9, 10, 11, and 12, and so on. Now, this is going to really help us weed out non-primes, and I'll show you what I mean. Starting right off the bat, we have a statement that 1 itself is not prime because we said it needs 2 factors, 1 only has 1 factor. So I'm going to take that and take that right out of consideration. Now, when I look at columns 2, 4, and 6, if you look down those columns, because of the way these columns have been set up, every number in those columns is in fact even. Well, 2 is our only even prime, so the rest of these, from 8 down to 98 in the second column, are all non-prime. Everything in column 4 that starts with a 4 down to 94 are not prime, and everything in column 6 are not prime. So we've now basically cut the numbers for consideration in half, but let's take this even further. We know that in column 3, 3 is a prime number, but if you take a look at the rest of the column, everything in there is in fact a multiple of 3, and there is our 51. Our 51 appears in this column, so that goes back to our last example where we're wondering whether 51 was prime. So in fact, everything in this column, other than the 3 at the top, is no longer in consideration. So now we've really dropped the numbers that could possibly be prime to about 1/3 of what they originally were. Now I'm going to build on the 5. 5 itself is prime, but any multiple of 5 ends in 5 or 0. So any number in column 1 and column 5, which are our only columns left, that ends in a 5 is in fact not prime because it's got a factor of 5. So I'm going to take out the 25, I'm going to take out the 55, I'm going to take out the 85. In addition, in column 5, I'm going to take out the 35, I'm going to take out the 65, and the 95. Now there are a couple more that still need to be eliminated. Numbers with double digits are multiples of 11, so I can drop 77 out of this. And then there are just a few more quirky ones that we need to eliminate. 7 times 13 is in fact 91. As well, 7 times 7 is 49. Once we've eliminated those, everything that is left, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97 are our prime numbers less than 100. Very slick and a nice quick way to find your prime numbers less than 100. That's all I'm going to talk about this math talk. I'm out of time.